let us talk about calculus. I guess you all are familiar with the equation of a line. We all have studied it in our school days, right? We write it something like y equals x, where if we have this line, then at every point on the line, the value of y depends on the value of x. For example, if x equals 2, then y equals 2, right? This relationship shows how y changes as x changes. But this kind of relationship is easy to visualize because it's a straight line, constant and predictable. Now, imagine you're a curious thinker in the 1600s, when the world was just beginning to explore the motion of planets, the falling of objects, and how things move and change over time. Straight lines didn't cut it anymore. Things in nature didn't always behave predictably or move in straight lines. Think of a ball rolling down a hill or water flowing into a basin. How do we even begin to describe such motion mathematically? Let's go back to the straight line for a moment. A straight line has a very special property. It has a constant slope. The slope tells us how steep the line is. That is how much y changes when x changes. For y equals x, the slope is 1, meaning for every one step forward in x, y goes up by 1, right? Now consider another line, y equals 2 times x. The slope of this line is 2, meaning that for every one step forward in x, y now goes up by 2. In other words, this line is much steeper than the first one. Therefore, slope is like a measure of the line's steepness. It tells us how fast y is changing compared to x. Now, imagine a situation where the slope is 0. For instance, if you have a line like y equals 3, a horizontal line, then we know that the slope of this line is 0, because y doesn't change at all, no matter how much x changes. On the other hand, if the slope is a very large number, the line is super steep, almost vertical. I think you understood my point. But then, someone like Galileo might come along and say, what about something like y equals x squared? That's not a straight line. It's a curve. For example, we all know that distance equals speed into time. Now assume you are running at a constant speed, say 2 meters per second. So d will now be equal to 2t, where d is the distance and t is the time, right? Now if I draw this graph where I put time on x-axis and distance on y-axis, then we get this straight line, and the slope of this line will be the same as your constant speed of 2. But now, assume you start running in a race, and instead of maintaining a constant speed, you begin slowly and then gradually speed up. At first, you might cover only 1 meter in the first second, which is equal to this point, then 3 meters in the second second, and perhaps 6 meters in the third second. The distance you cover is no longer proportional to time, and the graph of distance versus time will no longer be a straight line. It will be a curve. In this case, your speed, or the slope of the graph, or the steepness of the curve, keeps changing. At the start, your speed or the slope is small because you're running slowly. As you speed up, the slope becomes steeper, showing that the distance you cover in each second is increasing. Therefore, at any given moment, the slope of the curve represents your speed at that exact point in time. Back in the 1600s, this was a huge problem. The slope wasn't constant anymore. People could draw the curve, but they had no idea how to calculate the slope at any specific point on it. And then came geniuses like Isaac Newton and Gottfried Wilhelm Leibniz in the late 1600s. Both of them, working separately, came up with a groundbreaking idea. Instead of thinking about the whole curve at once, they zoomed in really close, so close that the curve looked almost like a straight line. This is how the concept of the derivative was born. We all know that if we have 2 points like this on a straight line, then its slope is given as y, 2 minus y, 1 over x, 2 minus x, 1. Newton and Leibniz realized that to find the slope of a curve, you could look at 2 points getting closer and closer together, such that they could find the exact slope at a single point. But how does it work? Let us understand this with an example. Suppose we have a curve y equals x squared. Now, if we want to find the slope of this curve at, say, x equals 1, then assume we take 2 points, where the first point is obviously 1, and 1 square, or 1 itself. And then let us take another very close point, say x equals 1.1, and y equals 1.1 square, or 1.21. Now these 2 points are so close to each other that the curve here behaves almost as a straight line. So what will be the value of this slope? It will be this minus this over 1.1 minus 1, right? This gives the value of slope at this point as 2.1. This is simply amazing. Now let us level up our gear a bit more. Assume we have a point as x and the y value as x square, and another point at some distance h from x, say x plus h, such that its y value will be x plus h whole square. So, now, what will be the slope of this line? It will be x plus h whole square minus x square over x plus h minus x. Look at the denominator. X will get cancelled out, and we are only left with h. Now, expand the numerator to get this as x square plus 2x times h plus h square and minus this x square. Oh, look, now x square will get cancelled out, and we are left with 2x times h plus h square over h. Divide it properly to remove h from the denominator, and we are left with 2x plus h. Here comes the magic. We want both these points to be as close as possible, which means this h is so small that it is almost invisible to our naked eye. Thus we say that h tends to 0, and since h is not exactly 0, we put this lim here, which stands for limit, which means what is the value of this thing when h is very close to 0, and to solve for it, we put h as 0, which gives us 2x as the slope of the curve y equals x square. So we say that the derivative of y, which is represented using dy over dx, which indicates the change in y with respect to x at a given point, is 2x when y equals x square. Now at x equals 1, what will be the derivative of y with respect to x? Or in other words, what will be the slope of this curve at x equals 1? Just substitute x as 1 here, and we are done. The slope of this curve at x equals 1 is 2, right? We solved it previously and got our answer as 2.1, remember? Which was so close to 2, but not exactly 2, because the value of h was 0.1, which, although small, but was not very close to 0. Now, to generalize this, instead of using x square, assume we denote y as a function of x or f of x. Now, at this point, x, we have y as f of x, and at this point, which is x plus h, we have y, or the output when the input is x plus h, as f of x plus h. So, the slope of this line will be f of x plus h minus f of x over x plus h minus x, right? This will get cancelled out, and we are left with f of x plus h minus f of x over h. Finally, we put a limit here which shows h tends to 0, and that's it. This is the derivative of the function y, or f of x, with respect to x. Now, using the method I have just shown you, mathematicians have already calculated derivatives of some famous functions like these. So our life has now become super easy. So, using this formula, or deriving on your own, now can tell me in the comments, what will be the derivative of the curve y equals x cubed at x equals 2? This simple idea of zooming in on a curve and finding its slope has transformed how we understand and solve problems in the world around us. Suddenly, derivatives became a universal language for describing change, and it is used in our day-to-day life, starting from measuring speed to predicting stock prices, tracking heart rate changes in medicine, and analyzing an athlete's speed during a race. They help in weather forecasting by predicting temperature changes, studying population growth in biology, answering questions like why planets orbit in ellipses, and calculating marginal costs in economics. Derivatives also control robotic movements, optimize traffic flow, enhance sound engineering, and even monitor the spread of diseases. Now, if this video gets 3,000 likes, then I will bring another banger video on calculus, which will be much more interesting than this one. So good!